It will come up again. So next week there will be, I appreciate if you read, there's going to be a lecture on antenna, which we didn't do so far because we have an expert on this. This is going to be done by Asim Kashi, and he will just give you a very nice introduction to that. I thought it was a good idea. So if you could join, it would be good if some people were there because you would be lost if nobody's there. It's just, I can do that for just the video, but you probably wouldn't like that. Where are we? What we were learning last time was the basics of field effect transistors, and I think some of you know this already in a way. So it is very clear what we need for digital. That's something. Let's see whether this is well running. And there was this outrageous scaling we had in Moore's law, and we ended up with very small devices. And what we are learning today now is why that was good also for microwaves, in what sense, and that helps you maybe also to gain a little bit of understanding for good microwave devices. So some things we did in this course are very useful for microwaves, others not so much. And what was particularly good was this principle of currentless control in a MOSFET. So if you find a device which actually can be controlled without a current, that is of course quite good. So this principle that we have not a fast that we not have a junction at the gate, at the control contract, that in itself is a major driver. So when you, because these are essentially ohmic contacts and then PN contacts, they are slow. So if we use those also for the gate control, this will kill our performance of the switch, and then related also to the just see whether this is transported. Also see whether this is going to be whether this is going to be also done for the gate contact, then you are slowing yourself down. So with a junction FET, you will have trouble in reaching a speed of microwaves at all. That in itself is important. So the MOSFET only works because of the MOS gate. Yeah, so that's the principle, because the moment you put in a current, then you're in trouble. That's important that you understand that part. For the FETs, we said some things that we have. For FETs, we have quite some choices. That is maybe not so clear, so I want to explain that again. So the normal MOSFET we use is an NMOS. The reason is that this is the faster one. Yeah, so for microwaves we use NMOS. So electrons are in the channel, induced by inversion. Yeah, and also typically there are enhancement type, which is something different. So enhancement type means you need a positive voltage to turn the device on. Yeah, and it will be off if nothing happens. This is so self-control. So think of it to fail. Yeah, nothing is there as a voltage. The device is automatically off, which is a good thing. Yeah? So that helps a lot. And for example, why is this might be problematic? For example, for if you have an N channel but a depletion type, then you need a voltage just to keep it off, which normally is an additional effort. Yeah? So that's not so nice. However, most of the good microwave devices are actually depletion types for physical reasons. So when we do many good devices, they are N-type, but they are normally on. Yeah, so you get for you can change the polarity of the current. We normally don't like that because of the P channel is indeed not so good in mobility, first of all, and also in carrier density. So that means that you can do the same thing with the P-channel enhancement type, and if you combine that with an N-channel enhancement type, you actually get a fully complementary logic. And that's very nice. That is what CMOS does. Yeah? And then there's, of course, the depletion type for P-channel that has mainly only disadvantages. Hope this is clear. Now what we need for microwaves. So let's get away a bit from the digital idea. So what do we want as for carriers or for microwave FETs? And the one idea is clearly that you want a very high concentration of the carriers in the channel. Yeah? So you want to modulate a lot of devices because it has it's two advantages. One is that you advance the current, so you get more current. It's also, and this is also good because you have to, easily get a very low resistance with that. That's helpful. Yeah? And then something which and you know from CMOS maybe there are scaling rules that with every node you go down, the current slightly goes up. So the maximum current you get per node is always slightly increasing because you reduce the channel length. Yeah? And that is clear. If the channel length is reduced, then you typically also get a higher current. Yeah? What you also get is, of course, when you reduce the channel length, you also typically get a lower voltage, which is then the drawback. Yeah? And you want what comes along with this high current drive is that you want low parasitic elements. Yeah, and this is something the CMOS community, so the digital people do extremely nice because they want to switch fast. Yeah, so they have these very nice connection structures which are very low in their capacitive behavior and also in their inductive behavior. Yeah, so there's all kinds of resistance. So I've taken out the mean ones which we always are concerned about. The first thing is if you are here, if you have a MOSFET, but if the metal on top over the MOSFET is very, very lossy, that in itself also constitutes a loss. So you have to charge and discharge this resistance. So you don't want that. You want a very good material. Yeah? So that's typically what you want. Because it's the input, when you think of it dynamically, it's the input of the FET. And if you have to drive any AC wise, we have a current which is going in, and this one should go through a resistor which is in series, but this has to be low, otherwise you are lossy. Yeah? And then of course we like very small gate length because the transit times are short and the capacitances are going down. Yeah? That's helpful. The trouble with this is if you put many carriers in the channel, you also have to make sure that there's no breakdown. So the voltage limitation is, as I said, a bit critical. We have to think about that. So what is helpful, this is a device which you probably haven't used in your life yet, but it's the most simple one just to tell you how people started. Yeah? So this is a MESFET. Yeah? This is not even, it's similar to a MOSFET, but it doesn't have an MOS gate. It has a metal gate. Yeah? So it has a Schottky contact. It's not a junction gate, but a Schottky gate at the gate contact. And as we learned last time, the Schottky gate is a unipolar gate, which is capacitively quite good. Yeah? So this charges fast. Yeah? And why did people do that? Is essentially you take a layer of a good material like gallium arsenide, you do a bit of implantation here. Yeah? So in the channel regime, you put some metal on top with a Schottky contact, and you can control the flow of the carriers in the gallium arsenide. So very simple. Yeah? So it's just and these additional layers are only added to make sure that there's enough doping under the source and drain metal to make sure the current is flowing. That's quite simple. So it's a MESFET. There's no heteroepitaxy. It's a bulk device. It's relatively simple. And the reason I mention it at all is this is how Wi-Fi started. So the initial Wi-Fi devices were, nobody had a good microwave FET, but they had gallium arsenide and they just needed 5 gigahertz. You know, from the beginning, Wi-Fi was at 2.4 and at 5 gigahertz. And they just did it. And what you learn from that is that the complexity of making this device is relatively low. So you have that particular wafer, you implant, put some metals, that's it. It's not cheap because, as you know, a Wi-Fi adapter cannot cost a fortune. Yeah. And it was on a good substrate that also helped a lot because the gallium arsenide, which we have in the background here, so the substrate itself, that was is particularly isolating. So this is a perfect waveguide. So the gallium arsenide, when you take the right one, it is a very low loss isolator. So it's a very nice substrate, but it's contrary to silicon, it's very low in conduction. So 10 to the 10 ohms or so. So really low. So that helped. And then, but that wouldn't work, and what is driving is the efficiency now. So people use these MOSFETs, and they realized they weren't getting any efficiencies which they liked. So the things were drawing too much power, and then people thought about it, and then then you now understand why I'm talking about heterostructures. This is also not a very advanced device. It's the same idea. It's now this high electron mobility transistor, which is based on the MOSFET. So it again has a Schottky gate, so a unipolar gate, just a metal on top of a layer. Yeah, and you have the same structures as before. So you have some layers here which make good contact, so they are highly doped. And the difference is what we already talked about is that they use this principle of a barrier between the Schottky contact and the channel. So the channel originally was gallium arsenide. So here, at some point in time, people also moved to an even higher mobility material, but it's not a change. It's just a small modification. The principal change is what we already discussed was that you put a barrier between the channel and the Schottky gate. Welcome. Just join. And the idea is that you use now this barrier with the wider band gap of this material here. So you put L gas, yeah, on top of gas. This is this heterostructure growth where you get an additional barrier. Yeah? And the trick was that they also now, remember my example of the motorway. If you don't dope the motorway, it's a good motorway, but you have no cars. And here it's now realized that you put a silicon doping in this barrier, which is not conducting. So the barrier is a material where you don't want the transport. So the only thing where the barrier transports is to get it to the channel here. So this works if you do it right. But you don't want any transport here below the gate. You only want it in the channel. So this is this tube idea. So you have a tube, and you want under the gate you just put the carriers, but not in the layer where you transport. That's the principle of the hand. And high electron mobility is because the channel itself is undoped, very, very non-doped at all. But you have carriers, and where do you get the carriers from? You make a layer sequence, and if you put these dopants, now we call that delta doping, so you just make the channel, you put something on top, and then just in the right distance, you put silicon as much as you can, and then what happens, this is quite simple. We put them here in this barrier, yeah, but we are not doping the channel, and we just make sure they get close so that they can tunnel. Yeah? So this is a generic quantum effect which we use there. Yeah? And just to tell you, this is very useful. You have been using it today. The speed advantage we get is to make sure we get, this is mainly for the backbone of the internet. So when you leave the base station, you talk to the base station when you talk. Yeah? So this is very clear. You have your cell phone, but then the data is aggregated and sent out maybe from the base station to the nearest fiber. Yeah? And this is typically done by point-to-point links at a relatively high frequency to get the bandwidth. Yeah? And these devices are those which you use to connect to the internet. So you're not directly connecting, but your base station approach just exactly does that. Yeah? And it tells you why we need these quantum effects, is that only because of the separation of the carriers from which you transport from their doping rumps, as we say, so these reminders where the silicon is still sitting without the electrons. Only this enables this performance. Yeah? So this is physics. And why does it work so well? Because the carriers tunnel, they stay here. And the modulation efficiency, as we say, so how well can we modulate those carriers in the channel? So how easy is that? Yeah? And in a way, it's not, although the MOSFET is of a different type, it's a similar idea to the MOSFET, because the MOSFET also has not a barrier, it has an oxide. And very near to that, you can modulate a sheet of carriers. So it's the physics is actually a bit different, because in the MOSFET we have this inversion, which we don't have here. Yeah? Here we have just plainly doped carriers in a normal material. No PN, nothing, just one type, completely unipolar. Yeah? But it's the same idea. You have a contact, something which separates them. And then the carriers, there's no current flowing into the gate, also here. So this is very efficient. Yeah? The advantage why we use these transistors in comparison to silicon, even if we have the same gate length, is they have a lot more voltage capability. Yeah? So because the band gaps we have in all those materials here, gallium arsenide and AlGaAs, are way higher than in silicon. So the voltage capability of this is typically 3 or 4 times higher. So you get this, get the same speed, but you have much more voltage. Yeah? There are some characteristics which are universal for the FET, which is something one can know or should know. This is, for example, here that the current near the threshold, as we say, when it's turning on, is a quadratic function of the control voltage. Yeah? So it goes up in a quadratic way. So there's a pinch-off voltage here, or threshold voltage, yeah? And it's turning on in the sense that every FET on this planet turns on in a square wave, in a square fashion versus voltage. Yeah? So that's what you can say. And there are now various plots you can make. So transfer characteristic is output current over input voltage. That's simple. And the output characteristic is output current over output voltage. So that's also makes some sense. And then the trick is now when you now talk about speed is, or what makes our life easy in the modulation, is to have a strong change of the output bound current to the input voltage. So the stronger the output current reacts to the input voltage, the better. Yeah? And there you also see some reason why we increase the current. Yeah? Because when you take this, you can form it back and think how the current change would work with current itself. Yeah? And you see it's increasing, not linear, but at least when we have a higher current, we also get a little bit more of transconductance. So that's very simple. That's not rocket science. It's so true for every transistor in this universe. And it just says that the transconductance increases also, among other things, with the absolute current level you are in. Yeah? So this gives you some guidance. And the other thing is, what we don't want is that the output current changes with the output voltage, because the transistor principle is always, it is GM positively forward by GDS. So if you have GDS very low, so that the current is not changing, then you get a good gain. Gain is always forward divided by what's going backwards. That is a very fundamental idea. So it's not like an AC where you just think forward and don't reflect that there's a large wave at the output and this has also impact to the input. We tend to forget that, and the idea is always that you want that the transistors only work because in this, let's see whether I have the plot. You have seen this plot many times in your life. So there's the transconductance or the transfer, which is the output current over input voltage. And the reason why this finally is power amplifying is you have here a current change, and then you want the voltage to swing. Yeah? And what should not happen, what happens here is if the current is changing, that there's also a voltage change. The dynamic effect is based on the idea that this is a flat line essentially. So it is a high resistance at the output, which means that there's no change in the voltage statically with the current. So it stays statically and then it swings. That is a bit strange, but it's always this idea forward in comparison to what's going back. So you don't want that to change. And that is important. Now we also sometimes look at a bit more what can we now do to improve things. This is also very generic, so you can easily look at that. The first thing is that this transconductance, which we are dreaming of to be high, and it's good that it's high. So there's a couple of items which we can, there's the gate width. So a larger transistor has, so if we make a big area transistor, it has a larger transconductance because the absolute current is changing and is also, of course, changing linearly with the width. However, why doesn't this affect speed? Because there's also the same way the capacitance goes also up. So this is not really something where we can optimize the technology. Yeah? So this is not helpful. Yeah? What is helpful are these three parameters: the effective velocity in the channel. So which velocity, which material in the channel should I use to make this thing fast? And that is easy. That is what we did here. So I told you, people originally looked at gallium arsenide, and then they realized if they added another indium atom again in a very nice layer, then this effective velocity is just higher. So that's why they came up with this idea. So it has a lower effective mass then, and then it's also much more mobile, so it has better mobility. So this carrier, so this is where which you introduce by material selection. So you take a better material and then you're speeding up. Yeah? And in this way, at ERF, we make some of the fastest transistors on this planet. And the reason why we can do that is because we optimize this parameter quite strongly. Yeah? So that's the idea. The other thing is, two things which we already mentioned, is there's the effective distance of the carriers from the gate. Yeah? So I told you always this example. This is not what I mean. I cannot control the people in the back of this room. If they're here, they're closer. Yeah? And so it is the same what you know from CMOS, where you have channel separation or oxide thickness. Yeah? So if the oxide thickness, or here in this case, it's the distance of these carriers from this gate, yeah, you want to get that closer. So that increases also your control. So you can control the current better if you're getting closer. Yeah? What is the drawback of making the oxide thinner and thinner and thinner? Maybe you know that already. Yeah. So you always have to think that you just want to keep that fat functional. So if you make it too thin, then the electrons they just say, well, so it's a bit countering the argument. If they can go from here to enter the channel, at some point they can also go in here and enter the gate. So if you make that too easy, then it's not good. So that's something where you have to be a bit careful that you don't overstress that argument. So you have to maintain a certain distance to keep things under control. Otherwise you have leakage, and that was the beginning of what I said. We don't want a current flow there. If there's a tunneling current, the whole concept just blows. It doesn't work anymore. Yeah? And that's why, for example, I mentioned earlier in the lecture that we are not using this classical silicon dioxide silicon interface anymore. And that's the reason they realized they were getting too much leakage or tunneling current there. So they decided to put a high K dielectric. Yeah? And this is also an agreement what is here, because the reason why the GM went up is also depicted here, because the high K dielectric gives us an additional boost to the transconductance. Yeah, so if you have a higher dielectric constant in the oxide or in the related barrier, then you again get a better current change. Yeah? So you see that even here in the formula. And and I mentioned earlier that we want high carrier concentration or high sheet carrier concentration, and this is also seen here. Yeah, so this is a reference concentration, and if you increase that, this thing goes down, and so the overall GM also goes up. It's a bit strange formula, but it's okay. So what should we do? We should get the fat thin. Apart from the transconductance, we should put high carrier concentration. We should choose the right materials. Yeah? But there's also a drawback, because there's also not only the transconductance, but there's also the capacitive effect. So the trouble is the same way when the transconductance runs up. In a similar way, the both capacitances, which are also present, are also moving up. So they have very similar formula. So you see here for these two, you can, in a first glance, you can say this distance df and this df and hf, to put it, they're not fully identical, but they are distances of the carriers to the gate. Yeah. So the problem is that the moment when you increase the transconductance, you're also increasing the capacitance. Because if you put carriers nearer to a gate, it sounds like a contradiction. You can control them better, but you also get more capacitance. Yeah, so that's why we need people like you, who are not just one-dimensional and think, okay, there's a simple formula, we do it, and there's a bit of engineering required. And you see that everything works. So in the CGE, if I said in the first approach, it's not, this is already a more delicate formula, but in the first approach, you could say that the effective carrier distance from the channel to the gate is the same for these two. So these two cancel out. So the feedback capacitance is essentially a constant, which is nearly true. So you can discuss that, but it's a very weak function. So the feedback capacitance is just metals. Yeah? So that's the main problem. So what are we left with? So the only real way to reduce our capacitances is to reduce the gate length. And this is why the Moore's law has been so beneficial for microwaves. Yeah, because they did that all the time. They made the devices smaller, smaller, smaller for a very different reason. So they wanted to make the devices smaller, not the speed. But of course, it was useful to have faster processors. Yeah, that it's a byproduct, a desired byproduct, but it was not the original intention. But it's extremely beneficial for microwave performance on the speed side. Yeah, so that helps. And then comes the big problem, which CMOS is facing then. That's why we have other things like HEMT and others also on the agenda. When you this is now a MOSFET depicted, and this is a MOSFET, a relatively large one even, and you put that to a high voltage, 14 volts, yeah, and you see that the field distribution is here very clearly maximized in the PN region. So just like when we remember how the MOSFET would work, this is the polysilicon gate, there's the inversion happening here, and now the electrons travel, but if you increase the voltage, you get significant electric fields at this junction. And this is a real problem, because if they heat up too much, then they kill the MOSFET, and it's not only tunneling what happens then, but it's also damage to the oxide. Yeah, so this is really because it's so concentrated. And why is it concentrated here, the E field? Because you have that strong step of the P versus N region. Yeah, so you have this, when it goes from the P-doped region of the gate region to the N-doped. This is it's like a diode, which is a very located jump in the concentrations, and then this looks like that. Yeah, so this is really killing silicon CMOS in voltage. And it would look the very same if we went out to 22 nanometers, and a much smaller voltage would be the same problem. So we have a significant voltage problem. Yeah. For the Schottky's, we also have breakdown then, but the related breakdown is better, because what we can do easily, we are not putting everything into this oxide, and you see the difference here. Just for those who really want to go into the details, we can play with this layer here. We can change that distance and play with this transition a bit, and then we don't get such sharp profiles, so that we can engineer the whole story to a factor of 4, 5, 6 over silicon. So we don't have that particular hotspot. Yeah? So if you do this right, you can really get a large voltage swing. And for the same gate length, you get an advantage in terms of voltage. Okay. The other thing is, what I promised you is also that how does silicon do some other things. So silicon is very good in the reduction of the parasitics. So they have these very low loss environments which are reducing the parasitics, which makes them so speedy. Yeah? And we also do not, so for example, in the gallium arsenide, you can put a transmission line between the top and the back side of the substrate. So you can go through the gallium arsenide or the silicon carbide for other materials, because they're highly insulating. Yeah? The silicon itself is a very bad isolator. It's a conductor. Yeah? So it has a relatively high concentration of carriers. Yeah? And that is a problem, because if you modulate a wave now on the passive side through something which conducts, your wave will degrade quite strongly, which means very high attenuation. Yeah? So if you make that comparatively, that's a problem. Yeah? And that's why early in the process, people have used very different concept in silicon. They made these transmission lines on the top. So they're not going into the substrate. They keep the transistors, and next to them, they make other regions where they just make transmission lines from on top of the wafer, but at the stack. And the trick is a bit that if you have very thin layers, that's not so nice, because the impedances you get in the exercise, you do that, you shrink the things, and suddenly you realize the impedances you're getting then are not so nice. And that's the same here. So you can get silicon dioxide is a very low loss material itself, but the geometries don't fit, yeah, because this is only maybe 5 micron thick and not, as a normal wafer, 100 microns. So this is not giving you the right choice, but somehow it works. Yeah. So that's just to give you the flavor what you have, what are the differences also. Yeah. And as I said earlier, the people didn't do that in the beginning. They just looked at other materials and wanted to do things simple. Yeah. So they were just putting a simple gate, now back in gallium arsenide, on a substrate. This is now the MESFET. So you have, as I said, some doping profiles here and an implant layer in the channel region. So this classical MESFET, Schottky gate, yeah. And this also, you see that here from the dimensions, because the original WLAN, this requires some power. So you need 3, 4, 5 watts to power your WLAN at home. Yeah? So in this room, we cannot do this with a couple of milliwatt, because WLAN reception would be simply bad because of the propagation. The wave has to reach through this room and also hopefully through the door, that you have some WLAN reception beyond the door. And that's required. And you're seeing here that the transistors which we make then, they're relatively big. The structures, the gate structures are small, but the overall area is quite significant. So for the microwave devices, you can see them. Yeah, so this is 2 by nearly 1 millimeter. Yeah, so you have a physical vision of a transistor for this power level. Yeah? While for a silicon transistor, when we look at the gate, this was one transistor here in a cut, and they have only, you see the scales there, this is only 50 nanometers, so this you wouldn't really see optically anymore. Yeah? So, and you can of course make them larger for in all directions, but they were not developed to do that originally. The idea of a memory chip was to make a small function, so have a couple of micron length only. And here we have a couple of 100 microns of area. Yeah? So, and this is the difference in microwaves, because we cannot keep the power down because we simply have to reach distance. Yeah? And now let's show you also some. So I talked about this concept here. So we're making them, and then when you see what you really use today for the transport of your information on the backbone, and when you can see that how the base stations are made. There's a base station somewhere around here in the city, and they have these the slot antenna types which you talk to, and on top or bottom there's always the dishes. So there's always a second type of antenna, and this is where, and they also reach out, so they're reaching out for some kilometers to reach the next base station and so on. And what does that have to do with this plot? The plot is that we still have very small devices here in this regime to make them fast, but at the same time, we're also using this principle that we make relatively big transistors. Yeah? And here you can see that we have three advantages. You see here the device has it's not a small gate, but it's a reasonable gate, and it has a voltage capability of 15 volts here. Yeah? And then you see that such a transistor, even around 10 gigahertz, where we do some of this stuff, so the satellite communication, they're using this frequency, maybe 14 gigahertz, and the base station connections are then going up to, let's say, 30 gigahertz. They need power, and then you see here that they do power. So it's a single transistor provides you more than a watt of power, also at these frequencies. So this is, and here you see the difference between the gate length. So the length is this 0.35, 350 nanometers, so small but not too small. And the gate width is the sum of the third dimension. So what we see here, yeah. So we look now at the top from the transistor. So when we cut through any of these, we see this. So as before, yeah. So the gate length we cannot really see because it's 350 nanometers. That's below our vision, yeah. But the effective length of these fingers, they are millimeters. Yeah, so this is probably something like 4 or 5 millimeters overall in width. Yeah. Why do we put them in parallel? That's also something you need to understand. So we are now putting up multiple fingers next to each other. That has to do with the law of inductors. So if we make one, would we not make them parallel, but if we put them in one finger, the inductance on this would be way too high. And if you parallelize inductance, then getting down. So this inductance is kept low. And you can also see that from the wave perspective. That's probably easier to be understood. There's a wave coming in, and you need to keep the phase. Yeah? So the wavefront, the idea is you have a continuous phase, but it needs to be constant for everything you do. Yeah? Now you have one phase here, but part of the wave is amplified here. So there's some of this stuff is directly going through this part, and some of this takes this detour. Yeah? So if you're widening too much in terms of the wavelengths, that is not in phase anymore. Yeah? It would also not be in phase if we would make one single finger out of it, because if it was 1 millimeter long and the wave you would try to keep that in a phase, that doesn't work, because then here the beginning of the finger would not be in phase with something which travels over the finger with a changing phase, so you would not get a reasonable phase consistency anymore, because the power at some point has to be in phase still, and it adds up at some point. So here, that's why it's easier to understand it. Here you're going in, zero phase going through, but if you needed to take a detour here, to use this finger to increase the power, then there's a certain limit for these differences. Yeah.
Like more the parallel we have, the more it is difficult to
And that's working against us when we go to higher frequencies, because then geometrically it's getting tighter.
So the inductance also increases.
Yeah, the inductance is one way. First of all, you have to keep the inductance down. And the second, because on this bus you have to connect it in some way, so you have to keep, and so this line in itself forms an inductor. So that's a problem, which falsifies the phase. But it's really a challenge that because if the wavelength also reduces, you are geometrically not able to keep that in phase. So that when we go to higher frequency, smaller wavelength, the transistors also shrink. Yeah? Which directly means you don't have so much area, and area is power because area is current. So that's why we have higher losses at higher frequencies. And at the same time, we have to keep the devices, make them smaller. And this is a double contradiction. You have harder opposition and you have less forces to counter them. So both things are working against us. So this is why it's such a challenge with your 5G phones, which you have in your pockets, to go from 3 or 6 gigahertz to 28 gigahertz. It's really a problem because you want this to work also when it's raining. And so like on a day-to-day, we have humidity like hell. And then when it starts raining, or in the morning, we all got a shower, then you have to make sure that still the power goes through the very bad atmosphere. Yeah? So you need power, otherwise it doesn't work. Okay, so this is the FET side, and the FET side works reasonably well. But there's also another, don't be disrupted by the gate, there's also another link which fits to the day today. I like that. We also can use the bipolars. Yeah, so we saw the bipolars are a bit critical because when we use PN junctions, they are not necessarily fast. Yeah. So we said as a junction gate, to use them as a gate contact, that's probably not the smartest thing on the planet to do, because PN junctions by definition are slow. But we can, using PN junction, we can build something which fits very much to the weather. Yeah, so that's the important idea. And what is the big advantage of bipolars is that you have two carrier types, yeah, which goes for a reasonable amount of current, which is good. So you have, remember in the FET we wanted high currents. And that probably what you also can achieve with a bipolar. Yeah. The first question always is, why on earth does a bipolar work? And I was so frustrated when I was a student that nobody explained the bipolar well. It's always bad. Because it's essentially then, they all come with this idea. You have two of these diodes. So the first thing is you have an NP here, in just this case an NP region, which, as you know, is a PN diode. Yeah? And it always frustrated me that when people said, so the NPN structure, which then forms a transistor, is actually a nightmare, because we learned that diodes are in one direction useful, there's send current, and the other one they cut current. Yeah? So if we now double this structure, why on earth should there be a current flow apart from a leakage? Yeah? So there's no way you can send any reasonable current through that structure if you have NPN or PNP, because they're just opposite diodes. And if they are done well, there's no current flow at all. What helps is to know something which you already know, which is that there is a second principle in these transistors, is that the flow of current is not only based on fields as done with the field effect transistors, because there we take a field and modulate a carrier density of one type, and that actually changes a current flow. Yeah? But you remember there's a relatively strong effect which is related to this diffusion thing. So this diffusion forces are relatively strong. Yeah? So, you know, let's go to the swimming pool now, put ink in this water, and in relatively short time, the whole pool is blue. And that we know. It's a relatively strong thing, which it works against the concentrations. Yeah? So in the case, we can organize strong concentration changes. Then things are working well for us because strong concentration changes induce carrier flow, additional carrier flow. And that's interesting because if you think that idea from what we did here, we always wanted to have a high GM. So we want a strong current change. Yeah? And why on earth should this work? So first on the top, so we take these two diodes and you're essentially building two barriers. So in no way there's a current flow possible because these are two inverted diodes. Yeah? But what is good now, and this helps you now to understand the bipolar, is the idea of this water slide. Yeah, because there's an analogy which I think is best from the possible explanations I found. If you are in a swimming pool, you're sitting on top of a slide. You're not moving yet. Yeah? But the idea here is that when you're sitting on top of this water slide, when you start, you kick yourself off with a relatively minor motion. So you're just sitting there looking at this pool, waving, and then you make a click, and then whoosh. You're going down the slide, and that's very attractive. And this is exactly the consequence of this bipolar flow, that you only need a relatively minor kick to get yourself into the water. Yeah? And the reason is the difference in the dopings. Yeah? Because there's one consequence when a dipolar starts to fly is that we make strong changes of the emitter doping profile, which we put high in N. We put the base, which we later call base, high in P, and the collector again high in N. And because of that, we have a relatively strong additional support of the carriers leaving the emitter. So they want to get out of there because they have there's too many of them and they want to follow this concentration gradient. Yeah? And because of this urgency, there's a relatively minor voltage change or current change needed at the base to make that happen. Yeah, so there is this additional support which gets them into the base. Yeah? And the moment they do that, you have to observe one thing, that this only works if you make things relatively small. Yeah? So the idea is that this base, so it's not just two remote PN junctions, but it's getting them together, yeah, close to each other. So you can induce a carrier flow by increasing making very sharp profiles and getting the electrons into that base. Yeah? And the trick is then that at some point they diffuse further and then they're caught by the relatively strong field of you sliding down the water wave, the water slide. Yeah? So it's this little kick, and if it catches you, you're going down a very long slide. Yeah? And that is the reason why we have an additional effect which favors so much the amplification. Yeah? It's this combination of sharp profiles, which induced by diffusion, plus proximity to a second PN junction. And as you know, once you kick yourself, whether the slide is long and takes, let's say, a kilometer, I think the longest one can be really a kilometer, the point I'm trying to make is it's more or less independent. Yeah, so you have gotten this kick, and then you travel, and finally you splash into the water. This is the same you can engineer here. So whether this is a relatively steep slide, or whether you then turn a long way through the water slide is independent. Yeah, so, and of course, if the slide is not so strong, then the voltage capability of that bipolar is good at the output. Yeah? So you have a relatively minor kick on the current because of the diffusion, and you can independently organize how long the slide is, which essentially is determined by this profile of the doping here. So here we make that sharp. Here there's still a very high concentration in the base. But then we have things we have a high concentration, but how we organize the collector profile with the N doping is something you can do more or less independent. So you can really do that nicely. You know? So that's as far as it takes. So you have a small, and that leads to very nice properties of the bipolar. There's one problem with that water slide experiment, which is a bit strange. There's a second current, which is not important, but the thing we have to understand is that on the back side of your water slide, there's also people creeping up the slide on the other side. That is a bit strange, so that doesn't fit into our image. So we normally think that the electrons are traveling down on the top side, but there's also another current coming from the collector into the emitter, which is supportive. It's not so strong. But if it's just working this way, it's fine. So that's possible. So it's an additional feature because it's bipolar. So there's this red. This is a bit strange, so it's good to understand what happens. But people creeping on the other side of the slide up the hill, that's a bit. But that's physics, so it just happens. Yeah. How did people start that? It's again similar to the MESFET that helps you to understand why people are doing this. So in the first place, they took a silicon wafer and they did implants. Yeah, so you shoot implants, that's the concentration in certain areas. You take an emitter, highly doped area, a base, and then this subcollector finally to the collector contact. Yeah. And you can just easily organize a distance. So essentially, if I give you a piece of paper, you could tell a process engineer in the IMTech clean room what to do. You could do that. It's not difficult. Yeah? You are already now capable of do some engineering, and it would probably work. Yeah? Just to put it into perspective, these particular transistors flew to the moon 50 years ago. Yeah? So just to give you an idea. So that it is also the simplicity in the engineering for the reward you get. Yeah. So the Moonlink was an S-band link. So that's 2 to 4 gigahertz. So they needed relatively high amplification and also power because they had to go through the atmosphere to the moon and back, which needs power. So it's not just something you can do. But it was a relatively simple concept, so not much. And the only thing they had to do then is to put metal contacts on base, emitter, and collector. So you see, this is something you can essentially do already. What do we get now? And that's something which helps you now to understand why we are discussing the bipolar at all. We have CMOS, so it's all complementary FET, so we don't need that. But there's something fundamentally good, which is the reduced current amplification of the bipolar. Yeah? And in this common emitter configuration, so this is source as input, gate as or base as the controlling gate, and collector as the receiving contact. That's the common emitter configuration. You compare the collector current, so the controlled current, by the control current by the base current, so to say. Yeah? And the question is, what do you get then? Yeah? So, and this is what you see here. And the bipolar, you have to check very carefully. This is again an input voltage plot. So there's an input voltage given, and you plot now two currents, the base current and the collector current. And what you see is that the important thing, what you see here is that the both currents are put to an exponential scale. So these differences are not linear; they are exponential. logarithmic question is how you write it. So it means that the base current is by orders of magnitude lower than the collector current, which means that you have a very, very high current amplification. And you can, and this plot is named after Hermann Gummel, a person at Bell Labs somewhere at a time. And you can see here, he had this idea. So if you just have the collector current and you plot it this way, so here you have 10 to the, what is it, 10 to the 5. You see this correctly? So this is 11, 9, 7, 5, and minus 3. So let's take 10 to the minus 5, and the base current is related is 10 to the minus 9. So you get, for this reading, directly a relation between these currents of more than 1,000. And that's a lot of current amplification. Yeah? So you get a very high amount of current amplification through this principle of this additional contribution from the diffusion part, so not just field-controlled carriers, but also diffusion-controlled carriers, which enable a much better current flow because the electrons want to leave the emitter and just need a slight kick to go up there. This is the current amplification, and you still get through this collector engineering for the speed this thing has a relatively decent voltage swing. Yeah? So you can say now 1.8 volt is not really a lot for the in terms of voltage swing, but for the speed you get in relation because of the high current gain, you win. Yeah, so it's always voltage per speed, and the related CMOS device would have a lot less voltage swing. There's also one drawback of the bipolar. You have to be a bit careful with the temperature, because a bipolar transistor in large amounts of this output field here, of output characteristic, has a positive temperature coefficient. And that's a bit ugly because when you produce current, what will happen? More current will produce more heat. And if more heat produces then again more current, which is the meaning of this positive temperature coefficient, that's dangerous because you get in a positive accelerated loop of current generation, and that's what's happening here. So if you're not careful and don't have a measure to reduce that, there's an easy way to design that, but you have to be careful, because otherwise, if you're here and then you're heating and it's heating up and then you're on an exponential curve, and then your cell phone amplifier would explode. It's a very simple trick, because if you put a slight resistance to the base in the right way, just the right value, if it's heating up, this resistance will increase a bit and will control the base current so that you're moving a bit down here. So this, if you adjust this correctly, you have to think of it. If you miss that, then the whole thing blows through the roof. If you get it, then you're in good shape, because then you can make use of these nice characteristics here of the device. What is the application? I think I've mentioned this a lot of time, but it's just good to mention it again. This part is bipolar transistor. And the reason is because of this high current amplification. We also get area-wise, if you think of absolute current now, you see this device is really small. Yeah, so it's a couple of micrometer square. And we can get a lot of current in a small area. This is exactly what we need in these, because they should fit in our pocket relatively. Yeah. It's a stupid argument, it's not very scientific, but it's what I'm representing by that is a volume density for current. Yeah. And we always, it's true, we made that example. If you build this with FETs, you get a tablet. You can, of course, argue a tablet is nicer than a cell phone, but it gives you a flavor of the because you can get the same transconductance also with a FET, but you need a lot more area. So that's why, and the reason is that this bipolar principle, which we just talked about here, this is a really efficient physical drive. So it helps a lot to use this second current creating mechanism. You could say it's only a stupid physics thing, but if you think what you find attractive in these, you think it has to be smaller, it has to be maybe the display bigger, but it needs more performance, so functions should be smaller. That's how we trigger. Yeah? So, and this is not, of course, not only, this is just a stupid commercial example. It's true for every of those appliances. If you're building an airplane, a satellite, a car, a ship, you always have these issues with the weight and the associated volume of something. Yeah? So this is good. Then there was a second Nobel Prize winning idea, and that is why we also look at these heterostructures in the vertical dimension, because there's some trouble with this doping. Yeah? So at some point, when we already discussed that in parts, when we use that argument to get the electrons out of the emitter into the base, that's fine. Unfortunately, when you do the same thing with the holes in the base, they also want to leave. Yeah, so the trick is, if you dope, you want to get the base highly doped as possible, because we want to have this difference in our favor. But the problem is that there's two types of ink now. There's the blue ink going into the pool, and there's another ink which will kill what we just achieved. And you can see that here in the Gummel plot. Yeah? So you see, this is the electrons we want to leave the emitter, so going down the slide. The trouble is, there's the control. If we have too many p carriers in the base, then the kick I need to move is getting larger and larger. So I'm losing my advantage. So if I'm not careful with this doping, this B curve, IB curve, goes up. So I'm losing my particular advantage. And because of the progress, this is the Nobel Prize of something 2000 something, somebody had an idea to introduce also a vertical barrier. Yeah? So in this case, so we know this barrier already here for the electrons, but we are not using now this as a channel, but we're using the other thing, that we're looking to the conduction band here. Sorry, to the valence band. And in the valence band, it's always a bit strange because you have to think differently. So here in the conduction band, this is a barrier, yeah? And for holes going down in the energy band is a barrier. Yeah? And by putting now this emitter into a second barrier, so we take a larger band gap device here. So we're not taking gallium arsenide as we did originally, but we're taking something with a wider band gap. We build another barrier here for the holes. So the electrons can still tunnel nicely into the base, as we just explained, also with the support of diffusion, but they cannot so nicely mount this energy barrier into the emitter, which would increase the base current and would kill our current performance, current amplification. Yeah? Because this ratio, then you can really show that if you compare devices with such a barrier and without, you can get the same current, but you simply get different levels of leakage. Yeah? And this is what Herbert Krömer at the time found, and he proposed that, and they invented the natural bipolar transistor, which is what we are using here. So I don't know how many 30 billions of such transistors in every cell phone we have on this planet. Yeah? So it's just this idea which is in there. So this is the most used microwave device on this planet, and for that reason. We have it in every cell phone, and every one of us has about 100 in them just the 100 is because this, I think I mentioned it in the beginning, this is not only useful for one standard or one band, you have all the bands from 2G to 5G in here by now. So this is now the big thing. So this barrier works very much in our favor. And that's nice. So this is the Nobel Prize winning idea, and here this is just to wrap it up how it looks. So this is invariance. So here's the current coming down. This is the emitter, which is doped, but there's the heterointerface here. Here is the control current, which we include here. This is a very small region here to keep it fast. This is to have the kick very low, no resistance and everything. And these things we get, and they get with every year, they still get 1-2% better in efficiency. It's just a slight optimization of the same principle. And that's why this is essentially why your cell phone survives the day, because the leakage you imply here is very low. And when it's operated, it's just perfectly working. So that's a good reason. And it's now it works well to 3 gigahertz. Now you have the smart idea you want to have more bandwidth. So the same devices now have to work for 6 and 28 gigahertz. And it's always a challenge because the efficiencies at high frequencies are very bad. So, and you still, if you use now the same modem for 3 gigahertz and 28 gigahertz, you would expect that it doesn't matter. So it should not kill your battery when you have a speedy data link. So you would still expect any of the follow-ups of these to work in a very similar way as it did before, just with much more performance. And how does that performance work? We have bandwidth to 3 gigahertz or to 6 gigahertz with the bands associated. And if they are full, so then somebody promised you more capacity, so we add another link at 28. And then we need again a device which at 28 gigahertz gives us a very similar performance. And this is why so many people are still thinking about that problem. It's a drive. And here, that's now a very smart joint. This is something which the silicon people are using. This is, you see, this is gallium arsenide because it's still the superiority of the material. There's no silicon in these here, so it's just apart from doping them, it's a fully 3-5 system. So the materials are still dominant. So there's no silicon or silicon germanium bipolar here. However, there's another region where we use that. So what people do in addition to use the same principle now in silicon with silicon germanium to help the CMOS get more voltage. And what you can do, this is very, very nice, is to combine those. So you make one area of the wafer with CMOS and FETs for digital and for all the functions, and another area you take just for bipolars, for RF. So that's one thing you can do. And then you can also use the very nice characteristics of, you can use all the technology modules from CMOS, which have been developed. And this is then how such a bipolar transistor can also look like if it's fully planar. So you see looks much more like a CMOS stack, not a silicon stack, it's not such a root. This is relatively root what we have here, just a few layers and a very powerful device. But here we have integrated that into the silicon environment now because we have all these nice modules from silicon. And here is then the silicon germanium bipolar transistor. So you have all the features from silicon, and then here a silicon germanium which is the base, and the silicon is the wide band gap. So this is the emitter. So we take a base, which is now, because silicon germanium has a smaller band gap than silicon, you get a heterostructure. So you get the same principle. So in this case, if you had it here, the emitter is silicon, has a wide band gap material, and the base is then silicon germanium has a band gap lower than 1.12 eV, and then you can still engineer the collector. And then you get very nice devices, and the integration, you see that here, this is also what I like. You can also see some principles in that. So you see that actual device is very small. So there's the base, the collector contact, and the emitter, very small. But all the other things we learned about can be really graphically seen. So for example, I told you maybe 30 minutes ago that the feedback capacity is essentially metal in a FET. And this is also true for the bipolar. You see what they do here? There's a base collector capacitance, which is the feedback capacitance. And how do they now reduce that capacitance? So they put the base contact in the third dimension to connect it, and the collector contact comes from the right. So there's a minimum overlap if you go 3D in this way. So there's the only overlapping element is about here. But this goes to the back and this goes to the side, not to have much capacitive coupling. You don't have to know much, you see that. You see also that we need to connect the emitter with high current, but we don't want to build an additional emitter base capacitance, which would be an input capacitance. So we again put this in this direction and take this from the left. You see also this is a small device and a big chunk of copper, which helps to get a lot of current in, keep the resistances low. But we also do this very intelligently, that we are not coupling too much. So that's just to give you a little bit of flavor how things can be done finally. And here this is then for example, some of the recent silicon germanium. So they're not, the transistors are not so small as the latest CMOS. So they're still in the range of 100 nanometers in relation to, as you know, CMOS in here has 5 nanometer of length. So they're still bigger, but they're speedy. Now let's talk a little bit about how you make a bipolar fast. That's quite easy. I mean, here you can see that you need to make the transit times through the layers just short. And the answer how you make them short is very simple. You just take thin layers. So if you're vertical, the optimization is quite simple. You just make thinner layers, so the travel time is just proportional to the layer thickness. Because what does a vertical device do? It promotes power through layers. And if the thickness of the layers is thinner, then it takes less time to do that. Okay, and then maybe also some criteria. This is a quite nice formula. So the current gain cutoff frequency of a bipolar is essentially the number of travel times through the layers. So this is adding up to this cutoff. So the inverse time for that would be just the sum of the time to travel through the individual layers. And now, how can you make the power frequency high in relation to this is the Fmax. The Fmax is the maximum frequency of oscillation of power. So we don't talk about, we have current gain for the FT, and we don't talk about voltage gain explicitly. We typically talk about power gains. It's the same, because power times current is voltage. Sorry, current times voltage is power. So we talk about current, and we need one other quantity. People have agreed to talk about power, not about voltage. So they invented this formula here. So if you have a relatively high current gain cutoff frequency, how do you get a very nice power gain cutoff frequency? It's simple. You need to, of course, a high current amplification is good. And then you have two additional parameters, which are not fully surprising. There is this is essentially the feedback capacitance. So this is this capacitance created here. And you see people obviously have done something to mitigate that. So they put two parallel metal passes, and they're not putting them in parallel because this is the way in and this is the way to control. So there's So this is forming this capacitor, number one. And the other thing is you want to have RBB. This is similar to the gate resistance. So this is essentially into the base, how much resistance in series do I see when I go in. And it's clear if I'm controlling by a current, then I want a very low resistance because otherwise I will kill my current. So I want to keep this low. And where do you see this here in this plot? That the RBB is low, so they are also taking some copper, and then it will broaden then here at the back. Just to have, you cannot really make this much wider here, because then you would again build capacitors, but we want this wide. And it's a detailed optimization. So here you can see really the 3D contradiction. So ideally the base contact would be wide to reduce the resistance, but at the same time you have to keep the junction capacitance to this side low. So there's a compromise. And so that's, yeah. So there you see the beauty of this. And if you do all this right, you can build a very nice. So there's still a race which whether the FET or the bipolar gives the best transistors on the planet. So I'm more a FET guy, but the bipolars are actually at the moment in terms of power they are better. The FETs, the best we can make on this planet, are faster. So FET is faster, bipolars are more powerful because they have more voltage. So that's the game. But it's fun to work on this. It's just like keeps you, if you're just up in front of the world's development, that's interesting. And we are now by the time these frequencies which we reach at the moment are at the terahertz regime. So it's not gigahertz anymore, but we are one step up. So the highest stuff we have access to. So the fastest FETs we can make at the moment, they have such an Fmax of more than 1 terahertz. So they still provide power gain at terahertz frequencies. That's really the forefront of research.
Now that we have reached the terahertz frequency, at what voltages are we operating with?
So that's a very smart question. So presently the transistors we use, they are operated at something like 0.7, 0.8 volts. And the bipolars are always a bit better, so they're a factor of 1.5, maybe 2 better. But they have the problem that they are not so speedy, so it's always a...
So in order to reach the terahertz frequencies, we are primarily doing FETs only, right?
No, it's just also the bipolars are also pretty good, so they also get gain, they get a bit more voltage gain, so it's a race. So it's essentially what it comes down to is always the engineering, how thin these layers can be. This is silicon, yeah. So there's also speedy variants of these ones. So yeah, so this is just gallium arsenide, but you can apply the same better materials we used for these hems also to the bipolars, and then you are also getting quite good speeds. Yeah, so that's. Yeah, so it's just to give you the first flavors. The race is open, and there is not the better one, and this is the smart move actually of silicon and germanium, heterobipolar. You use both. So this BiCMOS I was talking about, this is really the smart move because you take the best of both worlds. So you take, for digital, CMOS is clearly better, manually and all that, and for the RF part, bipolar for power is better, so you can do that. And you see it here, so it's fractions of the wafer. So, for example, where this is presently being used is in these advanced radars for the Teslas, for example. You have, you know that you need a lot of very good memory there just to do all this digital part, and the radars at the same time also have to be good. The drawback of this is simply that it needs a lot more processing because you have to do the processing for the memory and then add the processing for the RF on the same wafer. So complexity goes up, but they're very nice. So this BiCMOS is really giving you from a system idea gives you the best performance. That's not necessarily from the individual devices, but from the combined force you can create, because it's not just one device which helps, it helps, because you need all things, so it's always a trade. Okay. So that gives you a little bit of flavor what we are doing here, and it's numbers. Yeah, at the end of the day, it's always as you ask. So is it good enough? And it's never good enough, because what is driving us for data is just bandwidth. People have this crazy idea that you're getting faster, and then efficiency works heavily against us. So for example, just to give you a numbers, the efficiency beyond 100 gigahertz for power conversion is a few percent only. So we really essentially heat up these devices, they put out microwave power, but the conversion efficiency at anything beyond 100 gigahertz is really bad. And so it's less than 10%. So that's where you're seeing we are not yet at the end, although we always say we are good. This is great engineering, don't get it wrong, but there's still challenges, and that's why I'm emphasizing this so much, because the atmosphere is really a strong contender. These atmospheric conditions are strong. You need power. You need good noise. All these items. It's not easy. And why I'm insisting with this lecture so much is that there's all this nice system engineering, but it comes essentially down to the performance of the core device. If they are better, everything else is easier. That's why we are working. And there's a lot of people in Taiwan and everywhere sitting just to make these devices always a few percent better. On the average, 1% to 2% per year. They started low in the 20s. Now they are around 50, but then somebody says, okay, double the frequency, so you're back to a low number. So that's the game. But it's fun. You see me still enthusiastic. We are doing this, so that makes a lot of sense and fun. Okay. So I hope this is interesting, and you see there's not the solution, but there's a lot of solutions, and enabling things and new things are upcoming. So there's always new materials which help you to get better. Yeah? So silicon is not silicon anymore, it's silicon germanium with a lot of additions. Yeah? And there's of course all the chemistry, for example, when you, for example, why, for example, is it so critical to put high doping concentrations in a base? We didn't talk about this, but if you put too much of something, that just diffuses also physically. And it's not just the electrons diffusing or the holes, it's also, you simply cannot put one layer with high concentration and then next layer nothing. That's also where you see these principles of diffusing also working in a mechanical way. So you say everything all in and the next layer stop. And then nature says, wait a minute, we have some laws here. And it's very clear because you have a high concentration, so we can make very sharp changes, but not to zero. And that's what I meant. So this idea about the water slide is just like the better you can make these interfaces, the less power you need to go to the swimming pool and splash. So that's next time you're in the swimming pool and thinking about, I'm always doing that, and I'm always having fun. Just when I go there, just think about that. It's just like click. It helps. And it's physically very true, so it's not nonsense what I said. It's just a very good image. And also, when you maybe if you are in a park and you have different water slides, you understand you can go very steep, and the fun is short, but you can also go very wide. Takes a bit longer, but you have some voltage capability. Okay, so thanks for the. So if you can motivate some people also to join next week, there will be something on antenna, not me. Yasan will do that, and just maybe it's also interesting that you learn a little bit about that. We didn't do antennas, and he will give you some flavor also how to radiate into the air. And Okay, then see you in 2 weeks then. Thank you very much.